Hello everyone. Today we will study row space, column space, and null space. Before I introduce those spaces, let me show you some basic concept first. Let A be a m by m matrix, which means A has m rows and n columns. First of all, let me introduce row vectors of matrix A. Let R1 be the vector formed by the entries in the first row, A11, A12, A1n. Let R2 be the vector formed by the entries in the second row, A21, A22, A2n. And continue. Let Rm be the vector formed by the entries in the m row, AM1, AM2, AMm. These vectors, R1, R2, Rm, they are called the row vectors of matrix A. These vectors, R1, R2, Rm, they are called the row vectors of matrix A. And since each row vector here has n components, A11, A12 until A1n, since each row vector has n components, in matrix A, all row vectors R1, R2, Rm, they are vectors in Rn, since each vector has n components. A11, A12 until A1n, since each vector has n components, they are vectors in Rn. Next, let me introduce column vectors. Let C1 be the vector followed by the entries in the first column of matrix A, A11, A21, Am1. Let C2 be the vector followed by the entries in the second column of matrix A, A12, A22, Am2. And continue. Let Cn be the vector followed by entries in the n columns of matrix A, A1n, A2n, Amn. These vectors, C1, C2 until Cn, they are called the column vectors of matrix A. So the vector followed by the columns in matrix A, they are called the column vectors of matrix A. Since each column here has m components, since each column has m entries, these column vectors, C1, C2, Cn, they are vectors in Rm, since each vector has m entries. They are vectors in Rm. Next, let me introduce the row space, column space, and null space of matrix A. In matrix A, its row space is defined to be the vector space spanned by the row vectors R1, R2, Rm. In matrix A, its row space is defined to be the vector space spanned by the row vectors R1, R2, Rm. And similarly, in matrix A, its column space is defined to be the vector space spanned by the column vectors C1, C2, Cn. In matrix A, its column space is defined to be the vector space spanned by the column vectors C1, C2, Cn. And the null space of matrix A is defined to be the solution space of the homogeneous system AS equal to 0. The null space is defined to be the solution space of the homogeneous linear system AS equal to 0. Note, in the row space, since R1, R2, Rm, they are vectors in Rn, then the span of these vectors R1, R2, Rm is a subspace in Rm. Therefore, the row space of matrix A is a subspace of Rn. The row space of matrix A is a subspace in Rn. Since each vector R1, R2, Rm, they are vectors in Rn. And similarly, since the column vectors C1, C2, Cn, they are vectors in Rm. Since the column vectors C1, C2, Cn, they are vectors in Rm. So the span of these vectors C1, C2, Cn is a subspace in Rm. Therefore, the column space of matrix A is a subspace in Rm. column space of matrix A is a subspace in Rm. Since the column vectors C1, C2, Cn, they are vectors in Rm. Now, how about a null space? The null space of matrix A is what? It's the solution space of the homogeneous system A is equal to 0, which means it's the set of all x such that A is equal to 0. Now, what's the dimension of x? What's the dimension of x? We know that A is a m by m matrix. A is a m by m matrix. In order to multiply A by x, this x is a column vector. So it has only one column. How many rows does S have? In order to match the dimension, X must have n rows. So since X is a m by 1 column vector, X belongs to Rn. Since X is a m by 1 column vector, X belongs to Rn. So the null space of A is a set of X in Rn such that A is equal to 0. So, since each X is a vector in Rn, the null space of A is a subspace of Rn. The null space of A is a subspace in Rn. The null space of A is a subspace in Rn. Since each vector in the null space is a vector in Rn, the null space of A is a subspace in Rn. Next, let's look at an example. Let A be a 4 by 5 matrix. A has 4 rows and 5 columns. Let A be a 4 by 5 matrix. Find its row space, column space, and null space. Find the definition of row space. Row space is the span of the row vectors. So, the row space of matrix A is the span of the row vectors. It's the span of the row vectors. We have 4 row vectors. 1, 2, 1, 0, 1. 2, 1, negative 1, 1, 1. 0, 1, 1, 1, 3. And 4, 3, negative 1, 2, 3. That's the row space of matrix A. How about the column space? By definition of column space, we know that column space is the span of the column vectors. The column space is the span of the column vectors. So here we have 5 column vectors. 1, 2, 3, 4, 5. So the column space is the span of the column vectors. First column is 1, 2, 0, 4. Here we run a column vector, we run a vector in comma delimited form. In general, run a vector in comma delimited form. Second vector is 2, 1, 1, 3. Of course, we can also run a vector as a column vector, but here I run a vector in comma delimited form. If we run an answer as a column vector, that's okay. If we run a vector as a column vector, that's okay. 1, negative 1, 1, negative 1. Next vector is 0, 1, 1, 2. Next vector is 1, 1, 3, 3. That's the column space of matrix A. So here we can see that the row space is a subspace of R5. The column space is a subspace of R4, since each vector has 4 components. Next, let's find a null space. How can we find a null space? In order to find a null space, we know that null space is the solution space of this homogeneous system A is equal to 0. So in order to find a null space, I first of all set A is equal to 0. Then the augmented matrix of this system is 1, 2, 1, 0, 1 equal to 0. 2, 1, negative 1, 1, 1 equal to 0. 0, 1, 1, 1, 3 equal to 0. 4, 3, negative 1, 2, 3 equal to 0. That's the augmented matrix of this system. Then, reduce the system using the Gauss-Jordan elimination. Reduce the system using the Gauss-Jordan elimination. So let's reduce the matrix. In the first row, there's a leading one here. So I can multiply first row by negative 2, add it to the second row. First row stays the same. I get 1, 2, 1, 0, 1, 0. Multiply first row by negative 2, add it to the second row, I get 0. Negative 3, negative 3, 1, negative 1, 0. In the third row, there's a 0 here, so I leave it the same. In the fourth row, there's a 4 here, so I try to make it 0. So I multiply first row by negative 4, add it to the fourth row. Third row stays the same. I get 0, 1, 1, 1, 3, 0. The fourth row is 0, negative 5, negative 5, 2, negative 1, 0. Next, in the second row, I try to make the first non-zero entry to be a 1. To make it a little easier, I can switch row 2 and row 3. So interchange row 2 and row 3. First row is 1, 2, 1, 0, 1, 0. Switch row 2 and row 3. I get 0, 1, 1, 1, 3, 0. 0, negative 3, negative 3, 1, negative 1, 0. 0, negative 5, negative 5, 2, negative 1, 0. There's a leading one here. I try to make all entry above and below leading one to be 0. So I can multiply row 2 by negative 2, add it to row 1. So I get 1, 0, negative 1, negative 2, negative 5, and 0. Second row stays the same. I get 0, 1, 1, 1, 3, 0. On the third row, try to make 0 here. So I multiply second row by 3, add it to the third row. I get 0, 0, 0, 4, 8, 0. in the fourth row to make 0 here. So I multiply third row by 5, add it to the fourth row. Multiply second row by 5, add it to the fourth row. I get 0, 0, 0, 7, 14, and 0. Next, move to the third row. We try to make the first non-zero entry to be a 1. Here I can divide the third row by 4. So leave the first two rows the same. Divide the third row by 4. Let me copy the first two rows over. Multiply the third row by 4. Leave the first two rows the same. I get 1, 0, negative 1, negative 2, negative 5. That's the first row. Second row I get 0, 1, 1, 1, 3, 0. The third row is 0, 0, 0, 4, 8, 0. If I divide the third row by 4, I get 1, 2, 0. Leave the fourth row the same. In the fourth row I get 0, 0, 0, 7, 14, 0. Next, there's a leading one in the third row. In the third column, I try to make all entries above and below leading one to be 0. So what I can do here is I can multiply the third row by 2, add it to the first row. I get 1, 0, negative 1, 0, negative 1, 0. Next, I can multiply third row by negative 1, add it to the second row. I get 0, 1, 1, 0, 1, 0. And I leave the third row the same. I get 0, 0, 0, 1, 2, 0. Next, I can multiply the third row by negative 7, add it to the fourth row. I get 0, 0, 0, 0, 0, 0. The entire row is 0. Then change this back to equations. That's the reduced echelon form. Next, change this back to equation. Change the augmented matrix back to equation. In the first row, if I change it back to equation, I have S1 minus X3 minus S5 equal to 0. In the second row, I have S2 plus X3 plus S5 equal to 0. In the third row, I have X4 plus 2S5 equal to 0. Here, in the first column, second column, and the fourth column, there's a leading one. Those are leading variables. The free variable here is X3 and S5. The free variable is X3 and S5. Write X1, X2, S4 in terms of, next we write S1, S2, S4 in terms of the free variables. I have S1 equal to X3 plus S5. S2 equal to negative X3 minus S5. S4 equal to negative 2S5. Here the free variables X3, S5. So I pick any two variables for X3, S5. The X3 be T. The S5 be S. Then the solution space. Then a solution S1, S2, X3, S4, S5 can be written as S1 equal to X3 plus S5. That's T plus S. S2 equal to negative X3 minus S5. It's negative t minus s. x3 is a free variable, that equal to t. s4 is negative 2 s5. That's negative 2 times s. x5 is s. Here we have two variables, t and s. Then here I separate t and s in two columns. Next I separate t and s in two columns. In the first column I get t, negative t, 0, 0. If there's no t, write 0. Second column, I write s in the second column. I get s, negative s, 0, negative 2, and 1. Negative 2s and 1s. Next, pull out a variable. Pull out t and s. If I pull out t, I get 1, negative 1, 1, 0, 0. If I pull out s, I get 1, negative 1, 0, negative 2, 1. So, all solution can be written as a linear combination of these two vectors. All solutions can be written as a linear combination of these two vectors. So the null space is the span of these two vectors. First vector is 1, negative 1. Usually write a vector in comma delimited form. 1, negative 1, 1, 0, 0. Next vector is 1, negative 1, 0, negative 2, 1. That's the null space. So here we can see that finding the row space, column space, and null space is not hard. However, finding the basis is not easy. So my next question is, how do we find the basis for this vector space? How do we find the basis of the row space? Column space and the null space. In the above example. Finding the basis is not easy. Let me do the simplest one first, the null space. Let's try to find the basis for the null space first. That's the simplest one. What's the basis of the null space? We know that the null space is spanned by these two vectors. And these two vectors, they are not multiples of each other. If two vectors are not multiples of each other, then they are linearly independent. Since these two vectors spans the null space, and they are linearly independent, they form a basis of the null space. So that's the simplest. These two vectors form a basis of the null space. So the basis of the null space is these two vectors. 1, negative 1, 1, 0, 0. 1, negative 1, 0, negative 2, 1. So that's the simplest. That's the basis of the null space. But for basis of the null space, keep one idea in mind. Note, if we find the solution space of a homogeneous linear system, using above procedures, if we find a solution space of a homogeneous linear system using the above procedures, that means this procedure here, the vectors that span a solution space is always linearly independent. So if we find a solution space using this procedure here, the vectors that span the solution space is always linearly independent. Therefore, those vectors always form a basis of the solution space. Those bases always form a basis of the solution space. Since they are basis of the solution space, they are the basis of the null space. The general proof is very hard. The general proof for this statement is very hard. But here, let me at least show you some idea why is that true. In the previous example, when we are finding the solution space by reducing the augmented matrix to the reduced echelon form, we can see that here, in the third column and the fifth column, there are no leading ones. If there are no leading ones, we call x3 and x5 to be the free variables. We call x3 and x4 to be free variables. Here we let x3 be t and s5 be s. Then for the solution, x3 equal to t, s5 equal to s. In the third row, there's only one variable t. In the fifth row, there's only one variable s. Then I separate s and t. In the third row, I get t and 0. In the fifth row, I get 0 and s. Then I pull out t and s. In the third row, the entries is 1 in the first vector, 0 in the second vector. In the fifth row, we have 0 in the first vector, 1 in the second vector. Then here we can see that since in the third row there's a 1, there's a 0 here. No matter how, we cannot write 1 as a linear combination of zeros. No matter what we multiply to 0, we can never get 1. No matter how, we cannot write 1 as a linear combination of zeros. That means we cannot write the first vector v1 as a linear combination of the second vector v2. And similarly, on the fifth row, there's a 1 in the first vector. There's a 0 in the first vector. There's a 1 in the second vector. No matter how, we cannot write 1 as a linear combination of zeros. Which means, no matter how, we cannot write the second vector as a linear combination of the first vector. So these two vectors, they must be linearly independent. So, in general, when we are finding the solution space using this procedure, the vectors that span the solution space must be linearly independent. If we use this procedure, the vector that spans the solution space must be linearly independent. Therefore, this vector forms a basis of the solution space. And here we can also see that the number of vectors in the basis of the solution space is the same as the number of free variables. In this example, there are two free variables. We have two vectors in the basis of the solution space. And also, the number of free variables is the same as the number of columns without leading ones here. For this matrix, if we don't consider the last column, this is the reduced rational form of matrix A, which means in the reduced rational form of matrix A, if there are two columns with no leading ones, then there are two vectors in the basis of the solution space. So keep this idea in mind. The number of vectors in the basis of the solution space is the same as the number of columns that don't have a leading one. That don't have leading ones. In the reduced rational form of matrix A. On the other words, we can say that the dimension of the null space is the solution set of a homogeneous system. The dimension of the null space is the same as the number of columns without leading ones. In the reduced rational form of matrix A. So that's about the basis of the null space. Next, I'll show you how to find a basis of the row space step by step. Let's look at the theorem first. Let A be an m by m matrix. That means A has m rows and n columns. When performing an elementary row operation on A, the row space stays the same. Let's prove it. First of all, let R1, R2, Rm be row vectors of A. Since A is an m by m matrix, A has m rows, so there are m row vectors on A. Let S be the set of R1, R2, Rm. Let S be the set of all row vectors. Then the row space of A is span of S after performing an elementary operation on A. After performing an elementary operation on A, let V1, V2, Vm be the row vectors of the new matrix. After performing an elementary row operation, the dimension of A stays the same, still m rows and n columns. So we still have m row vectors. Let T be the set of V1, V2, Vm. Here we let T be the set of new row vectors. Let T be the set of new row vectors. Then the row space of the new matrix is span of T. So the row space of the new matrix is span of T. Next, we try to show that span of S is the same as span of T. Let's consider this in 3 cases, because there are 3 elementary operations. Case 1. If we interchange 2 rows, then V1 is the same as R1, V2 is the same as R2, but the ith row, Vi, will be Rj, and Vj will be Ri. If we interchange the ith row and the jth row, every row stays the same. Vi is the same as V1 is the same as R1, V2 is the same as R2, but Vi will be Rj, and Vj will be Ri, and the last row stays the same. Vm is the same as Rm. Since S and T contains exactly the same vectors, since S and T contains exactly the same vectors, because Ri still belong to T, Rj still belong to T. Since S and T contains exactly the same vectors, span of S equal to span of T. V1 is the same as R1, V2 is the same as R2, Vi is Rj, Vj is Ri, so Ri still belong to T, Rj still belong to T. All these R's, R1, R2, up to Rm, they all belong to T. So S and T contains exactly the same vectors. So span of S equal to span of T. If I interchange two rows, the element stays the same. So S and T, they are exactly the same. If S and T, they are exactly the same, span of S equal to span of T. That's case 1. When we interchange two rows, span of S equal to span of T. Case 2. If an operation is I multiply a row by a non-zero scalar, by a non-zero constant, if an operation is I multiply a row by a non-zero constant, by a non-zero scalar, if an operation is I multiply a row by a non-zero scalar, I try to show that span of S equal to span of T. How can we show that? If I multiply a row by K, then V1 is the same as R1, it stays the same. And the only change is an ith row. V2 is the same as R2. The only change is an ith row. Vi equal to K times Ri. In the new matrix, the ith row is K times Ri. And everything else stays the same. Vn equal to Rn, everything else stays the same. Here, since all vectors v1, v2, vi, vn, they can be noted as a linear combination of r1, r2, ri, rn, then span T is a subset of span S. Since v1, v2, vi, vn can all be written as a linear combination of R1, R2, Ri, Rn, then the span of these V's, span of T, is a subset of span of S. The span of the V's is a subset of the span of these R's, since all these V's can be noted as a linear combination of these R's. So span of these V's is a subset of span of these R's. And span of these V's is T. Span of these R's is S. And since Vi is K times Ri, and K is not zero, then Ri can be written as 1 over K times Vi. Ri can be written as 1 over K times Vi. And same thing here. R1 can be written as V1. R2 can be written as V2. Ri can be written as 1 over K times Vi. And Rn can be written as Vn. That means all R's, R1, R2, Rm, all R's, the index should be M here. And all R's can be written as a linear combination of all V's. So R1, R2, Ri, Rm can also be written as linear combination of v1, v2, vi, vn. Here, R1 can be written as V1, R2 can be written as V2, only for the ith row. Ri can be written as 1 over k times Vi. Ri can be written as 1 over k times Vi. And Rn can be written as Vn. So all its R's, R1, R2, Rm, can also be written as linear combination of V1, V2, Vi, Vm. Hence, the span of these vectors, of these R's, span of S, is a subset of span of T. Since span of T is a subset of span of S, and span of S is a subset of span of T, they must be the same. So span of S must be the same as span of T. Case 3. Another elementary operation is I can multiply a row by a constant added to a different row. Another operation is I can multiply a row by a constant added to another row. I can multiply the ith row by k added to the jth row. I can multiply the ith row by a constant added to the jth row. I can multiply a row by a constant added to another row. That's another elementary row operation. In this case, first row stays the same. V1 equal to R1. V2 equal to R2. The only change is the jth row. The ith row also stays the same. The only change is the jth row. Vj equal to k times Ri plus Rj. That's the only change. The only change is the jth row. I multiply k to the ith row, added to the jth row. Multiply the ith row by k, added to the jth row. That's the new jth row. That's the new jth row. And everything else stays the same. Vn equal to Rn. The only change is the jth row. I multiply the ith row by k, added to the jth row. The only change is the jth row. Here you can see that V1, V2, Vj, Vn, they are all linear combinations of R1, R2, Ri, Rj, Rm. Since V1, V2, Vj, Vm, here all index must be m. There are m rows. Can all be written as linear combination. Can all be written as linear combinations of R1, R2, Ri, Rj, Rm. Then the span of these vectors, the set of these vectors, the span of these vectors, v1, v2, vm, the span of these vectors, which is span of T, must be a subset of span of these vectors. Must be a subset of the span of these vectors R1, R2, Ri, Rj, Rm. This is set S. So here we show that span of T is a subset of span of S. Next, we will show that span of S is a subset of span of T. Here, since Vi Vj commuted as K times Ri plus Rj, then if I try to isolate Rj, Rj commuted as Vj minus K times Ri. If I try to isolate Rj commuted as Vj minus K times Ri. And also, since every row stays the same except the jth row, the ith row also stays the same. So Vi equal to Ri. Since Vi equal to Ri, then Ri and Vi they are exactly the same. I can replace Ri here with Vi. I can replace Ri with Vi. Then Rj equal to Vj minus K times Vi. So here I write Rj as a linear combination of Vi and Vj. Here I write Rj as a linear combination of Vi and Vj. Since every row stays the same except the jth row, and here I write Rj as a linear combination of Vi and Vj. That means all R's, all these vector R's, combined as a linear combination of these V's, of these vector V's. So all these vectors R1, R2, including Rj, Rm, can also be written as linear combinations of V1, V2, Vj, and Vm. Here, R1 computed as equal to V1, R2 equal to V2. Every row is the same, except the jth row. In the jth row, Rj equal to Vj minus K times Vi. I write Rj as a linear combination of Vi and Vj. That means all R's, including Rj, computed as a linear combination of V1, V2, Vj, Vm. Since all R's computed as a linear combination of these vectors V's, then the span of these R's, which is S, is a subset of the span of these V's, which is T. Since span of T is a subset of span of S, and span of S is a subset of span of T, they must be the same. Since in all three cases, we prove that span of S equal to span of T, then span S must be the same as span of T, which means the row space of matrix A is the same as the row space after performing an elementary row operation. The row space of matrix A, span S, must be the same as the row space of the new matrix after performing a row operation, span S. So, for any matrix A, when performing an elementary row operation, the row space stays the same. For any matrix, after performing an elementary row operation, the row space stays the same. But for this theorem, we must be very, very careful. This theorem is not true for column space. When performing an elementary row operation on A, the column space will be changed. The column space will be changed. Be very, very careful. Note. When performing an elementary operation, on a matrix, its row space stays the same. But its column space will be changed. Be very, very careful. Its column space will be changed. When we perform an operation, its column space will be changed. For example, think of this matrix. 1, 1, 0 in the first column, 0, 0, 1 in the second column. If I perform an elementary row operation on this matrix, for example, if I multiply first row by -1, add it to the second row, I get 1, 0, 0, 0, 0, 1. In the original matrix, the row vectors is 1, 1, 0, 0, 0, 1. So the column space is spanned by the column space is the span of these two vectors. 1, 1, 0 and 0, 0, 1. That's the original column space. This is an original column space. Now, for this new matrix, the column vector is 1, 0, 0, 0, 0, 1. So the column space is the span of these two vectors. 1, 0, 0 and 0, 0, 1. That's the new column space. After performing an elementary row operation, that's a new column space. They are not the same. They are not the same. For example, the vector 1, 1, 1, it can be written as 1 times 1, 1, 0 plus 1 times 0, 0, 1. The vector 1, 1, 1 can be written as 1 times 1, 1, 0 plus 1 times 0, 0, 1. So this vector 1, 1, 1 belongs to the original column space. However, this vector 1, 1, 1 no matter how, it cannot be written as any scalar times 1, 0, 0 plus any scalar times 0, 0, 1. Because in this vector, we have 1 in the middle component. But for these two vectors here, for both vectors, their middle component is 0. If I distribute k1 and k2, no matter what k1, k2 is, when I distribute, I get 0 here, 0 here. When I add, I get 0 in the middle component. So no matter how, I cannot write 1 as a linear combination of k1 times 0 plus k2 times 0. So this vector doesn't belong to the new column space. So 1, 1, 1 doesn't belong to the new column space. That means the original column space and the new column space, they are not the same, since they contain different vectors. These two column spaces are not the same. They are not the same. So by performing elimination operation on a matrix, its row space stays the same, but its column space will be changed. Be very, very careful. This theorem only works for row space. Next, based on the previous theorem, let me show you another theorem. It says, for all matrix A, let R be the reduced rational form of matrix A. Then, the set of all non-zero row vectors in R form a basis of the row space of A. This theorem says, the set of all non-zero row vectors in R forms a basis of the row space of A. The general proof of this theorem is very complicated. Here, I'll show you some basic idea about this theorem. So, let me use the previous example to explain to you. The previous example, A is a 4x5 matrix. So here, A is the matrix 1, 2, 1, 0, 1, 2, 1, negative 1, 1, 1, 0, 1, 1, 1, 3, 4, 3, negative 1, 2, 3. That's the matrix A. The first row is the first row vector. Let me call this vector R1. The second row is the second row vector. Let me call this vector R2. The third row is the third row vector. Let me call this vector R3. The fourth row is the fourth row vector. Let me call this vector R4. So the row space of matrix A is the vector space spanned by these four vectors. It's the vector space spanned by these four vectors, R1, R2, R3, R4. Let R be the reduced rational form of matrix A. What's the reduced rational form of matrix A? In the previous example, we actually reduced the matrices here. The reduced rational form of matrix A is this matrix, not including the last column. That's the reduced rational form of matrix A. That's 1, 0, negative 1, 0, negative 1 in the first row. 0, 1, 1, 0, 1. 0, 0, 0, 1, 2. 0, 0, 0, 0, 0. That's the reduced rational form of matrix A. Let me call the first column vector V1. The second column vector V2. The third column vector V3. The fourth column vector V4. The previous theorem, this theorem here says, the set of all non-zero row vectors in R form a basis of the row space of A. So this theorem says the set of all non-zero vectors in R. Here, V1 is non-zero, V2 is non-zero, V3 is non-zero, V4 is a zero vector, it doesn't count. So this theorem says the set V1, V2, V3 form a basis. It forms a basis of the row space of matrix A. That's what this theorem says. It says these three vectors form a basis of the row space of matrix A. But why is that true? Why V1, V2, V3 form a basis of the row space of matrix A? Why is that true? According to the previous theorem, we know that when we perform elementary row operation on A, the row space stays the same. So that means when we perform elementary operation, reduce A to the reduced rational form, the row space stays the same. According to the previous theorem, when we perform elementary operation, reduce A to the reduced rational form, the row space stays the same. So, according to the previous theorem, we know that according to the previous theorem, we know that the row space span of R1, R2, R3, R4 is the same as the row space of the new matrix, the span of V1, V2, V3, V4. The span of R1, R2, R3, R4 equal to the span of V1, V2, V3, V4. Since I can get R by performing elementary operation on matrix A. So they are exactly the same here. And here, V4 is a zero vector. V4 is a zero vector. That means this is a linearly dependent vector on the set. I can write V4 as a linear combination of V1, V2, V3. I can write V4 as a linear combination of V1, V2, V3. Then, by subtraction theorem, by plus-minus theorem, if I remove V4, the span of the set stays the same. So that equal to span of V1, V2, V3. By plus-minus theorem, since I can write V2 as a linear combination of V1, V2, V3. If I remove V4, the span of the set stays the same. So the set V1, V2, V3 spans the row space of matrix A. So here, V1, V2, V3 spans the row space of matrix A. Next, in order to show V1, V2, V3 is a basis, we must show that they are linearly independent. How can we show V1, V2, V3 they are linearly independent? Since this matrix is in a reduced rational form, in V1, if there's a leading one here, all entries below leading one must be zeros. In V1, if there's a leading one here, all entries below leading one must be zeros. Let's only consider V1, V2, V3. So let me temporarily cross out V4. We only consider V1, V2, V3. We try to show that they are linearly independent, which means we cannot write any vector in terms of the other vectors. So suppose here V1 has a leading one in the first column. That means all entries below leading one must be zero. That's a leading one. Since all entries below leading one are zero, there's no way I can write this leading one as a linear combination of these two zeros. There's no way I can write this leading one as a linear combination of these two zeros. That means V1 cannot be written as a linear combination of V2 and V3. And for V2, similarly for V2, there's a leading one here. All entries above and below leading one must be zero. All entries above or below leading one must be zero. That's a 1 here. There's no way I can write 1 as a linear combination of these two zeros, which means I cannot write V2 as a linear combination of V1 and V3. And similarly, for V3, there's a leading one here. All entries above leading one must be zero. Since there's no way I can write 1 as a linear combination of these two zeros, I cannot write V3 as a linear combination of V1 and V2. Therefore, for all these three vectors, I cannot write any vector as a linear combination of the other vectors. Then V1, V2, V3 form a linearly independent set. Since V1, V2, V3. Since each of V1, V2, V3 cannot be written as a linear combination of the others. Then V1, V2, V3, they must be linearly independent. Since V1, V2, V3 span the row space of A, and V1, V2, V3 they are linearly independent, then V1, V2, V3 must be a basis of the row space of A. Therefore, V1, V2, V3 is a basis of the row space of A. So, for all matrices in the reduced Gaussian form, the set of all non-zero row vectors, form a basis of the row space. That's what this theorem says. Next, based on this theorem, let's answer the previous question. The previous question was asking, find a basis of the row space. Let me first of all copy this row space over. The row space is spanned by these 4 vectors. Let me copy the row space over. In the previous example, the row space of matrix A is the span of these 4 vectors. It's the span of these 4 vectors. Let me copy this 4 vector over. First vector is 1, 2, 1, 0, 1. Second vector is 2, 1, negative 1, 1, 1. The third vector is 0, 1, 1, 3. And the fourth vector is 4, 3, negative 1, 2, 3. In order to find a basis of the span of these four row vectors, we first of all put these 4 vectors in rows. And form a matrix. I get 1, 2, 1, 0, 1. 2, 1, negative 1, 1, 1. 0, 1, 1, 1, 3. 4, 3, negative 1, 2, 3. Then reduce this matrix completely. Reduce this matrix to reduced Gaussian form. This matrix here is the same as matrix A. In the previous example, we actually reduced matrix A to the reduced Gaussian form. This is a matrix of matrix A in reduced Gaussian form, not including last column. Don't look at the last column. This is a matrix A in the reduced Gaussian form. So this matrix in the reduced Gaussian form is 1, 0, -1, 0, -1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 2, and 0, 0, 0, 0, 0. That's the reduced row echelon form. Then, according to this theorem, the set of all non-zero rows, the set of all non-zero row vectors in the reduced row echelon form form a basis of the row space. So that's a non-zero row vector. That's another non-zero row vector. That's another non-zero row vector. The last row doesn't count. This is a zero vector. It doesn't count. So the first three rows, they are non-zero row vectors. They form a basis of the row space of this vector space. So the basis of the row space of matrix A is the set of these three non-zero vectors. 1, 0, -1, 0, -1, 0, 1, 1, 0, 1, and 0, 0, 0, 1, 2. That's how we find the basis of the row space of a matrix A. We reduce the matrix to the reduced row echelon form. Reduce the matrix to the reduced row echelon form. Then pick the non-zero rows. The non-zero row vectors form a basis of the row space. That's how we find the row space. That's how we find the basis of the row space of a matrix. Next, let's continue. How do we find a basis of a column space of matrix A? Here, this is matrix A. Next is column space. I copy the column space and put it here. How do we find a basis for the column space? Here, column space is the span of these 5 vectors. How can we find a basis? We can apply the previous theorem. Treat each vector as a row vector. We can apply the previous theorem. We treat each vector as a row vector and put this vector in rows. I have 1, 2, 0, 4, 2, 1, 1, 3, 1, -1, 1, -1, 0, 1, 1, 2, 1, 1, 3, 3. If I put this vector in rows, now these vectors, they represent the row vectors of this matrix. Now these vectors, they represent the row vectors of this matrix. Then apply the previous theorem. If I reduce the matrix to the reduced row echelon form, the set of all non-zero row vectors form a basis of the row space of A. And the row space of this matrix, the basis of row space of this matrix is the basis of this set, of this vector space. So let's reduce it. That's the leading one here. We try to make all entries below leading one to be 0. So what I can do is I can multiply first row by -2, add it to the second row. I get 1, 2, 0, 4. Second row is 0, -3, 1, -8 plus 3 is -5. Then next I can multiply first row by -1, add it to the third row. I get 0, -3, 1. -4 plus -1 is -5. In the fourth row, we have a 1, we have a 0 here. So leave it the same. I get 0, 1, 1, 2. Next, for the fifth row, I can multiply first row by -1, add it to the fifth row. I get 0, -1, 3, -1. Next, in the second row, try to make the first non-zero entry to be a leading one here. What I can do is I can interchange row 2 and row 4. Interchange row 2 and row 4. First row stays the same. I get 1, 2, 0, 4. 0, 1, 1, 2. 0, -3, 1, 5. 0, -3, 1, 5. Last row is 0, -1, 3, -1. It should be -5 here. Next, let the leading one here. Try to make all entries above and below leading one to be 0. I can multiply second row by -2. Add it to the first row. I get 1, 0, -2, 0. Second row stays the same. I get 0, 1, 1, 2. Next, I multiply second row by 3, add it to the third row. I get 0, 0, 4, 1. Multiply the second row by 3, add it to the fourth row. I get 0, 0, 4, 1. Next, I can directly add a second row to the fifth row. I get 0, 0, 4, 1. Next, in the third row, try to make the first non-zero entry to be a 1. There's no other choice. I divide the third row by 4. So first row stays the same. I get 1, 0, -2, 0. Second row stays the same. I get 0, 1, 1, 2. Third row is 0, 0, 1 over 0, 0, 1, and 1 over 4. The fourth row is 0, 0, 4, 1. The fifth row is 0, 0, 4, 1. Next, let's a leading one. Try to make all entries above and below leading one to be 0. What I can do here is I can multiply the third row by 2, add it to the first row. I can multiply the third row by 2, add it to the first row. I get 1, 0, 0, half. Next, I try to make 0 here. I multiply third row by -1. Add it to the second row. I get 0, 1, 0, -1 over 4 plus 2 is 7 over 4. I leave the third row the same. I get 0, 0, 1, and 1 over 4. Next, I multiply the third row by -4. Add it to the fourth row. I get 0, 0, 0, 0. Do the same thing. Multiply the third row by -4. Add it to the fifth row. I get 0, 0, 0, 0. According to the previous theorem, the set of all non-zero row vectors in the reduced echelon form form a basis of the row space of the matrix. Those are the non-zero row vectors. These three are the non-zero row vectors. They form a basis. They form a basis of the row space of this matrix. And the row space of this matrix is the same as the span of these column vectors. So according to the previous theorem, the basis of the row space in the above matrix the row space of the above matrix is the set of all non-zero vectors 1, 0, 0, half, 0, 1, 0, 7 over 4, 0, 0, 1, 1 over 4. That's the basis of these row vectors. And this row vectors is the same as the span of these 5 vectors. That's the same as the column space of the original matrix A. So a basis of the column matrix of the column space of the matrix A is the same as this. So that's one way to find a basis of the column space of matrix A. But using this way to find a basis of the column space, it may be too much work, because for the same problem, we reduce the matrix twice. For the same problem, we reduce the matrix twice. For the same problem, for the same matrix A, we reduce matrix A twice. First time, reduce matrix A like this. The second time, we put a column vector in rows. That's the transpose of matrix A. We reduce the matrix in the second time. It may be too much work for one problem. Next, I'll show you a different way to find the column space. Let's look at the following theorem first. It says, for all matrix A, let R be the reduced rational form of matrix A. Then, in matrix R, for all columns that contain the leading one, the original column vectors in these places form a basis of the column space. So this theorem says, for all columns that contain the leading one in R, the original column vectors in these places form a basis of the column space. The general proof of this theorem is very hard. Here, I'll show some idea of this theorem. I'll show some idea of this theorem using the first example. In the first example, A is a 4×5 matrix. We try to find a basis of the column space. Using this theorem. So, this is matrix A. According to this theorem, we need to first of all reduce A to the reduced low echelon form. So this is matrix A. I copy it here. I copy the matrix here. The original column vector is C1, C2, C3, C4, C5. Those are the original column vectors. C1, C2, C3, C4, C5. I reduce A to the reduced low echelon form. I reduce A to the reduced low echelon form. That's matrix R. R is the reduced low echelon form of matrix A. The theorem says, in matrix R, for all columns that contains a leading one, the first column contains a leading one, the second column contains a leading one, the third column doesn't have a leading one, but the fourth column has a leading one. So this three column has a leading one. For all columns that contains a leading one, the original column vectors in these places, is this column vector, and this column vector. Those are the original column vectors in these places. First column, second column, and the fourth column. The theorem says the original column vectors in these places form a basis of the column space. So this theorem says C1, C2, C4 form a basis of the column space of matrix A. Why is that? We know that the column space of matrix A is the vector space spanned by these 5 vectors C1, C2, C3, C4, C5. The column space of matrix A is the vector space spanned by these 5 column vectors C1, C2, C3, C4, C5. Why its space is only these 3 vectors, C1, C2, C4? Why is that? In order to show this is a basis of the column space, let me first of all show that I can write C3 and C5 as a linear combination of C1, C2, and C4. Let me first of all show that C3 and C5 can be written as a linear combination of C1, C2, and C4. So I first of all set K1, C1 plus K2, C2 plus K4, C4 equal to C3. If I can find solutions for K1, K2, K4, that means I can write C3 as a linear combination of C1, C2, and C4. Now, let's set out these vector equations using augmented matrix. The augmented matrix of this vector equation is that I put C1 in the first column. Here, C1, C2, C4, they are vectors. I first of all put C1 in the first column. C1 is 1, 2, 0, 4. I put C2 in the second column. That's the augmented matrix of this vector equation. I put C2 in the second column. C2 is 2, 1, 1, 3. Next, I put C4 in the third column. Here, C4 is the third vector. I put C4 in the third column. C4 is 0, 1, 1, 2. Then I put C3 in the last column. Here, C3 is 1, negative 1, 1, negative 1. Next, reduce this matrix to the reduced low echelon form. Use Gauss-Jordan elimination. Reduce this matrix completely to the reduced low echelon form. if we compare this matrix with this matrix, we can see that all columns, the first column, second column, fourth column, third column, they are the same. So if I reduce this matrix, I must get a corresponding reduced matrix here. If I reduce this matrix, I must get a corresponding reduced Rorschach form here. So based on this matrix, the first column is 1, 0, 0, 0. The second column is 0, 1, 0, 0. The third column is C4. I get 0, 0, 1, 0. The last column is C3. I get -1, 1, 0, 0. That's the column in the reduced restaurant form. That's the corresponding columns in the reduced restaurant form. Since those columns are exactly the same, their corresponding columns in the reduced restaurant form must be exactly the same. And here we can see that this is in the reduced restaurant form. Then if we solve the equation, we can see that I get K1 equal to -1, K2 equal to 1, K3 equal to 0. That means I can write C3 as a linear combination of C1, C2, and C4, which means C3 is dependent, it's a dependent vector. Then by plus-minus theorem, in a span of a set, if I can write one vector as a linear combination of the other vectors, if I remove this vector, the span of the set stays the same. Since I can write C3 as a linear combination of C1, C2, C4, if I remove this vector C3 from the set, the span of the set stays the same. Next, I'll try to show that I can write C5 as a linear combination of C1, C2, and C4. So next, I set K1, C1 plus K2, C2 plus K4, C4. Here it should be K4. There's no K3 here. It should be K4. I said K1, C1 plus K2, C2, K4, C4 equal to C5. Next, I try to write down the augmented matrix of this vector equation. For the augmented matrix of this vector equation, I put C1 in the first column. That's 1, 2, 0, 4. Put C2 in the second column. I get 2, 1, 1, 3. Put C4 in the third column. I get 0, 1, 1, 2. Next, I put C5 in the last column. C4 is 1, 1, 3, 3. That's the augmented matrix of this vector equation. That's the augmented matrix of this vector equation. Next, use Gauss-Jordan elimination. Reduce this matrix to the reduced restaurant form. Use Gauss-Jordan elimination. We know that for this matrix, the first column is the same as this matrix. Second column is the same as the second column. The fourth column is the same as the fourth column. So the third column is the same as the fourth column. And the last column is the same as the last column. If I reduce the matrix, in the reduced restaurant form, it also must match the corresponding columns here. So for C1, the first column, if I reduce it, the first column is 1, 0, 0, 0. For C2, if I reduce it, its corresponding columns must be 0, 1, 0, 0. And for C4, if I reduce it, its corresponding columns must be 0, 0, 1, 0. And for C5, if I reduce it, its corresponding columns must be -1, 1, 2, 0. Then, based on this equation, we know that, based on the solution here, we know that K1 equal to -1, K2 equal to 1, K4 equal to 2, which means I can write C5 as a linear combination of C1, C2, C4. Since I can write C5 as a linear combination of C1, C2, C4, then by plus minus theorem, if I remove C5, the span of the set stays the same. If I remove C5 from the set, the span of the set stays the same. So, by plus minus theorem, we know that span of C1, C2, C3, C4, C5 is the same as span of C1, C2, C4. Next, we try to show this is the basis of the column space. That means we need to show that they are linearly independent. Here we just show that the column space is the span of C1, C2, C4. We just show that C1, C2, C4 spans the column space. Next, in order to show this is a basis, we must show that C1, C2, C4, they are linearly independent. We must show that C1, C2, C4, they are linearly independent. In order to show C1, C2, C4, they are linearly independent, we set C1, we set K1, C1 plus K2, C2 plus K4, C4 equal to 0. If I can show that K1 is 0, K2 is 0, K4 is 0, that means C1, C2, C4, they are linearly independent. Next, let's write this vector equation as an augmented matrix first. For the augmented matrix, I write C1 in the first column, C2 in the second column, C4 in the third column, and 0 in the last column. Here, C1 is 1, 2, 0, 4. C2 is 2, 1, 1, 3. C4 is 0, 1, 1, 2. Zero, 0, 0, 0. 0 is 0, 0, 0. Next, reduce the matrix to the reduced version form. If we apply the same operation here, from A to its reduced version form, if we apply the same operation here, the first column will be 1, 0, 0, 0. C1 will be 1, 0, 0, 0. C2 will be 0, 1, 0, 0. And C4 will be 0, 0, 1, 0. And 0, 0, 0 stays the same. If we use the same operation as I reduce A to the reduced version form, apply the same operations as reducing A. Do the same thing here. To be more accurate, apply the same operations as reducing A. We'll get the same column vectors. To be more accurate, let's say the same operations as reducing A. We get the same column vectors. We get the same corresponding column vectors. To be more accurate, we apply the same operations as reducing A. Then here we can see that here K1 is 0, K2 is 0, and K4 is 0. Since K1 is 0, K2 is 0, K4 is 0, that means C1, C2, C4, they must be linearly independent. Since C1, C2, C4 spans the column space and they are linearly independent, they form a basis of the column space. So C1, C2, C4 form a basis of the column space. That's this theorem. Next, let's apply this theorem to find the basis of the column space of this matrix A. The column space of matrix A is this. Let me copy and put it here. The column space of matrix A is the span of its 5 vectors. 1, 2, 0, 4. 2, 1, 1, 3. Next vector is 1, negative 1, 1, negative 1. Next vector is 0, 1, 1, 2. Next vector is 1, 1, 3, 3. In order to apply this theorem, I first of all put this vector in columns. In order to apply this theorem, I first of all put this vector in columns. So the first column is 1, 2, 0, 4. Second column is 2, 1, 1, 3. The third column is 1, negative 1, 1, negative 1. Next column is 0, 1, 1, 2. Next column is 1, 1, 3, 3. This is a science matrix A. This is a science matrix A. I put these 5 vectors in columns. That's a science matrix A. I treat this as column vectors. I treat this as column vectors. I put this vector in columns. So I get exactly the same as matrix A. Then apply Gauss short elimination. Reduce this matrix to the reduced echelon form. I actually reduced it already in the beginning. This matrix, ignore the last column. This is the reduced echelon form of matrix A. That's 1, 0, negative 1, 0, negative 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 2, and 0, 0, 0, 0, 0. According to this theorem, for all columns that contains a leading 1, first column, second column, and the fourth column that contain leading 1. That's leading 1, that's leading 1, that's leading 1. For all columns that contains a leading 1, the original column vectors in these places form a basis of the column space. The original column vectors in the first column is this. In the second column is this. In the fourth column is this. These 3 column vectors form a basis of the column space. So, by this theorem, the basis of the column space of an original matrix A is these 3 vectors. One, 2, 0, 4, 2, 1, 1, 3, 0, 1, 1, 2. That's the basis of a column space of matrix A. And this is the basis of a column space of matrix A. This is also a basis of a column space of matrix A. They are both bases of a column space of matrix A. How can we check that? First of all, we know that this set and then this set, they are both bases. That means they are all linearly independent. What's left is to show that the span of these vectors equal to the span of these three vectors. In order to show that they are both bases of the column space, we must show that span of this set equal to the span of this set. How can we show that the span of this set equal to the span of this set? We try to show that each vector in the first set belongs to the span of the second set. We try to show that each vector in the first set belongs to the span of the second set. And we try to show that each vector in the second set belongs to the span of the first set. So let's call this vector v1, v2, v3. Call this vector u1, u2, u3. We try to show that v1, v2, v3 belongs to the span of u1, u2, u3. That means span of v1, v2, v3 is a subset of span of u1, u2, u3. Next, try to show that u1, u2, u3 show that u1, u2, u3 belong to the span of v1, v2, v3. That means the span of u1, u2, u3 is a subset of span of v1, v2, v3. Since they are subsets of each other, they must be the same. That's how we show the span of two sets are exactly the same. That's how we show that the span of two sets are the same. I'll leave it for you to verify the answer. So I'll leave it for you to verify the answer. Next, if we compare this theorem with the earlier theorem here, we can see that we can use both theorems to find a basis of a span of a set. We can use both theorems to find a basis of a span of a set. But using the second theorem here, there is one advantage, which is that in the basis, it contains the same vector as the original set. In the basis, it contains the same vector from the original set. But using the earlier theorem, we can find a basis. But in the basis, it doesn't have the same vector as the original set. So that's one advantage of using the second theorem to find a basis. Next, let's reconsider the earlier question. Find a basis of the row space of matrix A using the original row vectors. That's the row space of matrix A. It's the span of these four vectors. They are row vectors of matrix A. How can we find a basis of the row space of matrix A using original row vectors? So, in order to find a basis using original vectors, we must consider the second theorem here. So, we must consider these vectors as column vectors. We must consider these vectors as column vectors. So, I put each vector in columns. Write it as 1, 2, 1, 0, 1. 2, 1, negative 1, 1, 1. 0, 1, 1, 1, 3. 4, 3, negative 1, 2, 3. Put each vector in columns. Then, those vectors, they are the column vectors of this matrix. These vectors, they are the column vectors of this matrix. Then I can use this theorem. I first of all reduce this matrix to the reduced row echelon form. This matrix to the reduced row echelon form. So reduce it to the reduced row echelon form. This matrix is the same as this matrix. We reduced it already. This is the reduced row echelon form of this matrix. So I can copy this matrix and put it here. I get 1, 0, 0, half. 0, 1, 0, 7 over 4. 0, 0, 1, 1 over 4. The other two rows are zeros. Then, by this theorem, we know that in R, in a reduced row echelon form, for all columns that contains a leading 1, that's a column that contains a leading 1. For all columns that contains a leading 1, the original column vectors in these places, they form a basis of the column space. These three vectors form a basis of the column space. Since I treat these as columns, these three vectors form a basis of the span of this set. So the basis of the above row space is these three vectors. 1, 2, 1, 0, 1. 2, 1, negative 1, 1, 1. 0, 1, 1, 1, 3. It contains the original row vectors. In the basis here, it contains only the original row vectors. So that's one advantage of using the second theorem.